Right, so in our ionic compounds part of learning, we learned that ionic compounds only dissolve in polar substances because polar substances can surround them and pull the ions out one at a time from the lattice. But we had trouble understanding what do we mean by polar and non-polar. In this, we're going to try to understand what is polar and what is non-polar. How can we use our understanding of electronegativity, our understanding of shape, and therefore our Lewis diagrams, put all of that together to say that's a polar molecule or that's not. The SciPad on page 60 explains it really, really nicely. It's got a very good explanation. This is sort of a summary of that and giving you a flow chart that you can play through in your mind to make a quick decision and then try to justify it using some key phrases to do with shape, charge distribution, and dipoles. And a dipole is a polar bond within the molecule. Okay, so it's within it. So the first thing we always look at is, does it have a lone pair of electrons around the central atom? So the key thing I'm looking at here is always going to be the central atom. This is why Lewis diagrams are so useful, because they will show us that straight away. If it's got a lone pair, it is polar. That's it. It is polar because it has an asymmetric shape, which means it doesn't have an even distribution of electrons. Right, so symmetric means that everything's the same in in 3 dimensions. Asymmetry is the opposite to that, so not symmetric. So if you think of a square, actually that's a bad example, if you think of a sphere, circle in 3 dimensions, that's completely symmetrical. If you then push in one side of it, it becomes asymmetrical. Good question. So an example I'm going to use here is ammonia. And ammonia has this Lewis structure. And we can see that around the central atom, it's got this lone pair of electrons. The name of that shape is trigonal pyramidal, or a trigonal pyramid. These electrons have pushed those hydrogens down. So if I drew it in 3 dimensions, it would look something like this. So that's not considered a symmetrical shape. In 3 dimensions, it has some symmetry around the triangle, but it doesn't have symmetry in 3 dimensions. So therefore, it will create a polarity. There is a dipole between these here, where the nitrogen creates a pull on the electrons because it's got a higher electronegativity, being further on the right of the periodic table. So therefore, if the electron's being pulled towards nitrogen and it's got the lone pair there, it has the electrons for much longer. So if it has the electrons for much longer, it's going to have a slight negative side to that molecule. So each of these bonds are considered a dipole. 2-pole is the hydrogens don't hold on to it for as long as the nitrogen. So this is slightly positive, slightly negative, slightly positive, slightly negative, slightly positive, slightly negative. It creates, those who like their physics, sort of a vector. So if I added those 3 vectors together, it would end up making a sum vector in that direction, straight up. So that would be our slightly negative side of the molecule, which means the bottom of it is slightly positive. Now those are a lowercase delta, in case it's hard to see. Basically draw an S and then bring the S around to touch the middle again, and you've drawn a lowercase delta. So these ones are probably the easiest. If you see a lone pair of electrons around the central atom, it has an asymmetric shape, it has to be polar. No ifs, buts, or maybes. To explain that, we need to then talk about the dipoles not cancelling out, and therefore where the slightly negative and the slightly positive sides of the molecule would be. But what if it doesn't have a lone pair, or 2 lone pairs even? Then we're over here and we have to look at, does it have any polar bonds? And polar bonds, remember, is when you have an electronegativity difference. So when one atom is more electronegative than the other. And it doesn't have to be very polar. It can be very, very similar. Well, if it doesn't have polar bonds, I'm going to give you an example where it doesn't equal 0, but it's close enough. The value's low enough that we can consider it's not polar bonds. It's got a symmetrical shape because it doesn't have a lone pair. Okay, so it does have symmetry of shape. And because there's no polar bonds in it, then all of the charge is distributed evenly because each atom is holding on to the electrons for the same amount of time. Now, the one I'm going to draw here has technically got polar bonds, but the difference in the electronegativity is so small that we sometimes consider it to be non-polar. And that's methane. Here's the Lewis structure. And chlorine, it's not chlorine, sorry. I was going to do a chlorine one down here. I'm getting ahead of myself. Carbon has got an electronegativity of 2.5. And hydrogen's got an electronegativity of 2.1. The difference between these two is only 0.4. That's low enough that we consider it to be a non-polar bond in year 12, not in year 13. Okay, but for year 12, that's considered to be a non-polar bond. For the purposes of teaching this, we'll use this one. You're very unlikely to get one that is a truly non-polar one in an exam because there's very few bonds between different atoms that are truly non-polar. Okay.
Do you get given the electronegativity?
No, you don't. So you need to look at where they are on the periodic table. Hydrogen's one of those special ones. I guess the key thing I want you to remember is that the hydrogen-carbon bond is usually considered to be a non-polar bond. Okay, it's probably the only one you need to know. Everything else, you use it. It'll be something in the top right-hand corner with something else. They'll be polar, with the one in the top right-hand corner being more electronegative, so having more pull on the electrons. Right, so the three-dimensional shape for this one. This is why we did our marshmallows thing. Has these evenly distributed in 3 dimensions.
What are those like lines in the triangle?
So the lines there are showing it going into the board. The triangle is showing it coming out of the board. Okay. So in here, our bond angles are all 109.5, which means it's symmetrical. There are no lone pairs. There are no truly polar bonds in here. So it's a symmetrical shape. The carbons and hydrogens are basically sharing the electrons evenly. Everything's balanced, so it'd be considered to be non-polar. This is incredibly rare. You're unlikely to get one of these as an example, as a question. But these two are very rare, are very common. Are the bonds the same? So for this one, I'm going to use two that look really similar. I'm going to use for my non-polar one CCl4 and for my non-polar CH2Cl2. So this one will be polar and this one will be non-polar. If we look at the central atom again, all of the bonds here are carbon to chlorine. So it's going to look identical to this, but with CCl bonds. The dipole created within each of those is the CCl bond. Chlorine is on the far right-hand side of the periodic table, so it's a very electronegative element. So therefore, that's going to pull on those electrons a bit more than the carbon and have them for longer. So each chlorine might be slightly negative and each carbon will be slightly positive. But when I put all of the other chlorines in here, they all pull the same amount. And so the net, again, for those that like their physics, the sum of these 4 vectors is going to be 0. They all add up to being nothing again. So therefore, the dipoles have cancelled each other out in 3-dimensional space.
Does that mean that that case will always have 4 things in it?
No, you could have something with, say, boron trifluoride, because boron only needs 3 things. You could have, for this one though, it's most likely, you could have BF3 or BCl3, something like that.
Why does that cancel out and that one doesn't?
Because boron only makes 3 covalent bonds, and then it's stable. So remember, it's one of the exceptions to the rule. Okay, but no, for most, you're quite right, it'll be 4 single bonds. So it'll be CCl4, CH4, CI4, something like that. Okay, because if you do anything else, although to be fair, CO2 would be another good example of this. what's that going to reach? No. So I'll put that up here, another colour. If I have CO2, then oxygen is more electronegative and electronegative. So I get those two dipoles being created. But that's quite obvious they cancel out, isn't it? Because they're the same. If it was a tug of war and they're pulling at the same force, then there's going to be no movement. So that's non-polar as well. Carbon dioxide is non-polar. So it can have double bonds in it, as long as they're the same bonds. Okay. And my last one is my polar. If I look at CH2, Cl2, it's really similar to this, but the difference is that each bond has got a slightly different pull on a slightly different dipole. So if I draw this one over here, if I just do the lowest structure first, there is a way to draw it where it looks like it's non-polar, because these two would cancel out and these two would cancel out. But we know that in 3 dimensions it doesn't look like that. So this is why we draw it. With our triangles and our dashed lines. The carbon has a bit of a pull on these electrons. The chlorine is more electronegative, so it has a pull there and there. And we end up creating a dipole. So we'd actually want to redraw that, because the negative side of the molecule is actually in the board. If you added all of those up, you end up then, because this is on an angle into the board, then you end up with the negative side being inside the board. So these ones, you need to sort of be able to imagine things in 3 dimensions. So you probably redraw this one. And the way you do it is you put something like CH2Cl2. What you do is you put your 2 more electronegative ones on the plane of the page. And then it becomes more obvious that the net of all of those arrows is going to be in that direction. If I added all those arrows up, it goes in this direction. So this side of the molecule would be slightly negative because it's pulling on electrons. Electrons are negative, which means this side of the molecule would be slightly positive.
How do you know that they're going to that direction?
Right, so this, when we did electronegativity, we learned that the ones on the top, on the right-hand side of the periodic table, were more electronegative than everything else.
Oh, yeah.
So they pull on it more.
But the little arrows, like...
Yep, so again, so chlorine is on the right-hand side of the periodic table. Carbon is more to the left than they are. So it goes away from the carbon to the chlorine. The chlorine's more electronegative. It pulls on the electrons more, creating these, what are called dipoles.
How do you know that it's negative on that side of the molecule?
Can you see where all those arrows are sort of heading in that sort of direction? If you put them all together. So you've got one going up there, then if I add that one onto it, and then add the next one, then add the next one, it's sort of all going in that direction. Yep, so adding arrows together, I can see that it's all going that way. That's showing the pull of electrons. Electrons have a negative charge, so it's pulling the negative charge that way, creating what we call a dipole for the molecule. It's a polar molecule. So a molecule like this, we could dissolve ionic substances into, because it can rip the ions out of the crystal, out of the lattice. Any other questions while that's still going?